Okay, we did some geometric constructions in the first lecture. We're going to kind of play physics backwards. What I'm going to show you today is a way to approach modern physics and improve on your classical underpinnings of modern physics using some very simple ideas. And if this is successful, I think the sort of thing that you're going to do today, which is derive basic relativity and begin the quantum mechanics, that in the next lecture, basically using a ruler and compass. And the hope is that we compress the knowledge that is collecting and making it so that you are usually 30 years old when you end your PhD and start your graduate. What I would like to show you is how this sort of advanced stuff could be brought all the way down to high school. In fact, there are things we're going to do today that do middle school. So if we're talking about something really simple that goes right to the heart of how things work in modern physics. And while we're doing that, we're going to learn about sin. The basic idea of this is that we have in the use of a calculator, there is always a sin button. And that's something that when you're just growing up and getting interested in science, it's a good thing to know about that button and all of the other ones. And it's basically the mechanism of this that is going to let us do what we want to do here. Now let me bring in something else here that I think is relevant to this, and that is, the best way to describe it is, I think, with a very famous movie. How many people have seen the movie called Men in Black, just out of curiosity? Let's see actual show of hands, because I've not seen it. Okay, I'll have to tell you a little bit more about it then. And you did, obviously. You, oh my goodness, you missed. You gotta look it up. Anyway, the basic idea is described, and let me go over to the, if I can here, I've got to find out where I am here, and I'll go over to the this guy right here. And by the way, I should go back on this slide before we go any further here, and show you the thing that you should look up when you want to start reading about this. It's called Chapter 0, and it's, I hope, going to be Chapter 0 of the Springer Encyclopedia of Atomic, Molecular, and Optical Physics. But anyway, this is where we talk about the fact that this whole of modern physics originates with two papers, 1900 Planck's, which we've already talked a little bit about in this class, and then the miracle year, 1905, as Einstein sort of revisiting stuff that was relevant to Planck, but not making connection, and doing special relativity. So, what I put here is, it is both of these story of light. It's let there be light, which is, everybody that knows the Bible knows that that was in there, right? And that is brilliant. But what comes after that, not so brilliant. But the idea of thinking of light is what we're going to be doing here. And I'm making the Men in Black analogy because one of the things that you see in that movie, if you look at it very closely, it probably went by fairly quickly when you saw the movie, is that she's carrying two textbooks. One of them is relativity, and the other is quantum physics. And so the basic idea that I'm putting out here is these both should be one book and a lot thinner. So that's what we're after here. But the other thing that's important, and that's what I'm
talking about here as well, is that most of the time, certainly in my education and probably yours, you grow up finding that books are intellectually richer than screenplays. But in this case, Men in Black would be a complete flop, as it were. The dynamics here is lost and static presentation. So what we're going to be using here, and it's really essential, is to show light in motion. A number of different ways, and then figure a way to get a roadmap of that motion using high school trigonometry. Okay. So let's proceed. I'll go back to just the lecture itself and point out, is a very short way to say what it is that I'm asking the readership to do, is head toward this direction of making the amount of stuff that we have to learn more concentrated and more available. So, everyone knows that sin is sine, and it's, we tell our home churched or home schooled kids that a sine is just the way they grade freeways. That is, the ratio of how much altitude you gain for a distance that you travel along a button. And it's so easy now to not have to look at a table. You push a button to get the numbers that go with that. And then there's another button right next to it usually. There's the complementary slope, and the cosine is part of our thing. Now, everything that we're going to be doing today is mostly about triangles. Sine and cosine, but lots of other functions in this. There are a whole bunch of functions that make a kind of a roadmap, and this is basic roadmap that we're going to use to develop modern physics. And the names for these things are appropriate. The secant is a distance that you cut into the circle. The tangent or cotangent are two sides of an actual tangent. This is the tangent, there's the cotangent. So, and then the cosecant is piercing from the other axis. So it's this complementarity of two axes that is very much a part of the geometry we'll be doing today, but certainly very obvious to draw the roadmap of sines and cosines and tangents, which we will be doing fairly shortly here. That's the beginning picture of what it is that we're beginning with. This is but there's a couple little funny things that are being done here. Instead of actually using angle, I mean the angle that I'm talking about here, and it's the angle of a favorite triangle, a 3-4-5 triangle. That's what we'll use today, is the 3-4-5 triangle. Okay. And we're talking about an angle 36.87, and that's kind of ugly. What we're really talking about is an area here. That little thing that we're going to be calling sigma, that's our angle, is going to be an area. It's an area of not just this sector, but twice that sector. It's what you get when you move a point here and open up, eventually, the whole circle. So when sigma gets to area pi for a unit circle, and here I have a radius b, but we're going to use the radius b equal 1 in almost everything we do, for a while anyway. That is the sort of the limit, 0 to pi. Of course, you can turn it inside out and go the other way, but we're not worried about that right now. Anyway, there are all of the trigonometric functions that you would learn in high school in their place in this sort of roadmap. And the idea of doing this is, well, let's go ahead here and get this on the other screens. And in particular, point out that you can animate any of these things that you have here on this particular beginning of the roadmap. Okay, and there's a more complicated thing down there, and what's more complicated is the fact that, and this is the other wrinkle that is really, I'm just amazed that this isn't in every book. It should be, but it just does not seem to be anywhere that I have found. And that is that we're also doing hyperbolic trigonometry with this roadmap. This is basically what it is. In other words, if I make, instead of a circle, x squared plus y squared equal radius squared, which is 1 here, I'm making a hyperbola, which is the flip of that, with a minus sign right there. Y squared minus x squared is equal to 1 here. And I'm tracking the area, the sector area of that, not just once, but twice. So 2 times that area right there, the stuff that's shaded in green, just like the red up here is doubled, so is that. So yeah, this is kind of the whole geometry that is the basic geometry that we're going to be talking about. But it's the basic trigonometry, the idea that the sine of that thing, and there it is hiding underneath the shaded region for the hyperbola, the sine of that thing is equal to the hyperbolic tangent of the green thing, the green area. And then flip it, the tangent of the sigma is the hyperbolic sine of the green thing, and so forth. They flip between each other a couple of times here. The secant of sigma is the hyperbolic cosh of the rho. Sigma rho, I use 2 Greek letters, one of them pointing this way and the other one turned over and pointing this way. Okay, and so it's these 2 that we're going to play with, either one of them. Now it's going to turn out that this one's associated with Doppler shift, and this would still be associated with a stellar aberration angle. They will be those things, roughly speaking. This is the logarithm of the Doppler. We'll get to that. But that's where this trigonometry map is so important to modern physics. Okay, so there's a lot of angles on this thing. It's very busy. There's the sigma angle right there. Well, it's not angle sigma, it's area of both sectors. And then this is an angle we don't use too much, nu. That's just the slope of the thing that we are thinking, just to bring it to something that you're more used to. Let's see if there's anything else I can say here at this point. All of the trigonometric functions and the hyperbolic trigonometric functions share sectors on here, just like that. And this is just a table of them. Okay, so it's kind of like these are cousins of each other: the secant and the cosine, or the cosh and the sec. You see, the hyperbolic cos is a sort of second cousin to the sec, but then the hyperbolic sec is the second cousin of the cosine. Then there's another pair right here, the cotangent and cosecant. They also have the same value: 1.333, 4/3, 5/3, 4/5 is shared by that, and so forth. Okay, so these are the numbers we'll use. Now, it's really nice to have it go at relativity, regardless of whether we discovered any of this, using fractions instead of decimals. That if you're going to teach this stuff, decimals, a bunch of decimals, you're not going to remember them, but these are much easier to, fathom, so to speak. Okay, and there's a more complicated drawing with everything going, the tangents and things. All of that, I mean the literal tangents, they are going to have, see if I've got this thing, I just moved it and that's what I want. That's what we're aiming at. So today we're going to construct a good part of that construction right there. And you see all the words that you've seen so far in this course. The only one that's there that you haven't seen much of is de Broglie wavelength. And phase velocity and group velocity, we've got to explain that. The Lagrangian and Hamiltonian are sitting there where they should sit in this wonderful roadmap that we're going to build today. You've been asking me what your final's going to be. It's going to be like what you're going to do today. You're going to have a graph just like this, and I'm going to give you a particular velocity, and you're going to work out all the functions. Okay? That's not such a bad fun. It'd be kind of fun, but you better practice. And that's what we're going to start today. Okay, let me go ahead and get everything sort of in the same direction here, because this is where we start. A little bit of algebra to remind you of what it is that we're dealing with here. And while we're at it, I'm going to put this computer onto that picture, which goes with that picture. We'll alternate between those. They are essentially the same picture, just we got to move the points around.
Professor Harter?
Yes.
If I may interject, you see how we measure here are areas oriented straight up. A trigonometer often measure their angles from the horizontal. That's the way the application does it. So they only differ between an inversion.
Yeah, thank you, TC.
A reflection around
that
that.
is the other wrinkle here, is instead of doing the Newtonian graph, where you plot x versus t in your calculus courses, right, I'm turning that. Okay, time is always going to be up or down, and space is going to be 3 dimensions perpendicular to that. We'll just work with one at a time. Okay, so, and that one is Minkowski, and we're going to mention Minkowski again today. So thank you, TC. That was an important point that we need to have. Okay, well, here's the algebra that we need to mention. Hypertrig comes next. But what I want to point out here, and we did this in Unit 1, Chapter 10, where we began the interest rate formula stuff and built an exponential and got all these series going. And what's neat about this, of course, is there are no imaginary numbers here. This is real. So in a sense, you really ought to work off the hyperbola first if you're going to teach trigonometry. The next step is to put the eye in and get the circular trig. To me, that comes second. So it turns out we're going to be mostly using this one, but there is a really funny way to do relativity that I'll get to, I hope, today. It uses circular trigonometry. And what we've done is married those two methods. Okay, and that just makes it richer and easier. Okay, see if I can get the next stop here is what we really need. And that's the other thing I didn't mention very much when I was going over the little Susie thing there, was that we have a name for what we're doing here, and that is relativity. Okay, this is going to be a new subject. It marries two things that really are, some people think as inimical, relativity and quantum mechanics. Certainly general relativity and quantum mechanics still are having a fight. But special relativity and quantum mechanics should not. They are the same thing if you look at them right. So I want to make sure that you know. The trouble with a new word like this is every time you type it, it's going to get an underline. It's going to say, hey, you misspelled relativity. Okay, I can put up with that for a while. We'll see how long it is. Now, here is a picture of a space-time gauge diagram, that the way I would draw it, and I just run out of space to put down an infinite number of phasors, but that's what we have. We have a wave that's varying continuously, and this is the wave, and then this is the wave, and then this is the imaginary part. Remember, proceeding. Imagination precedes reality by exactly 1/4 in the development of businesses, and that's a shame. But here is exactly what happens every time you have a laser make a coherent state that has cosine and sine waves, whatever you want to call them. They're moving at the speed of light. So all of these clocks here, the way this drawing is intended, are sitting there going around like phaser clocks. The real axis is up because it's pointing in the direction of the real wave, real psi, if you think of a psi wave. But we're thinking of a light wave here, and psi and E, except for units, are the same thing as far as we're concerned today. So we have a function here, and mostly we're interested in the quality of these waves. What color are they? How fast do they wiggle? How many wavelengths you can fit in a box? That's first quantization. But then there's this other number called the amplitude, and we're going to I'm going to kind of show you this today, but later on we're going to see it's a frequency too. Everything's a frequency, as it turns out, if you use the right unit. So the basic idea of a space-time plot of all of the things that a wave is doing, we're attempting to do it right here. And the phase velocity is just how fast a given phase moves. We'll say that again and again as we review this, but this is a really nice way to get at the whole idea of phases of waves. This is where the relativity really makes sense. And I would like to point out, and there's lots of links in this thing, and I see TC's put it over here, which is a good place for it. Let's start off with a European clock. See if this will work here. Yes. Okay, so here's the Earth turning, and there's the time. If we had matching zones all the way through most of the industrial world, those clocks are just as you show there, and this is a 24-hour clock. There's 12 hours, there's 24. And of course, there's always got to be a zero region there, so you can reach in here and set this thing to midnight, okay? So the Greenwich, England, is on the other side of this globe right now. It's midnight for them. You're looking like the sun coming. You are the sun shining on the earth. So right now it's high noon in little islands that sit out in here that the English didn't care about. So they wanted to put them as far away. They put them on the backside, okay? And then a little bit later, we get to noon. See if I can let this thing run until the noon shows up here. That was about there, right? Oh, come on. There we go. There we go. We're just about at noon, okay? And the wave is reading 12 is what we're very close to there. I should back it up a little bit. There's 12 right there. That's 12 noon right there for this little tiny country that started all this timing, right? UK, right? It's at noon, UK. All right? Well, that's one way to do it, but we don't do it that way. We have a 2-kink way for us, okay? And let me set this thing up and play the animation for this one. Okay, so now we have midnight and then noon and then midnight, just like they do everywhere else, but we read this, the clock reads the same at noon and midnight. Okay, so this is the wave with k equal 2. We're going to get used to wave vectors and stuff in just a minute here. So I thought you ought to see that just for the thing. Now this is a very old website that we made, 2005, the miracle year plus 100. Okay. All right. We'll talk more about that later. Anyway, let's go back to this and point out something else that's happening here. There are two extremes of a gauge field. The two extremes that you have are, first of all, the one where the clock frequency, okay, is 300 terahertz. That's our basic frequency that we're going to be plotting from, an infrared frequency. And the clock velocity, okay, the clocks that you're actually looking at here that are turning and giving you the time, are, attached to the Earth, basically. Their velocity is 0, and they have a frequency of 300 terahertz. And the other way to do it, and we're going to see that this is definitely the extreme of relativity, is to have the velocity of the clocks. The actual clocks are careening along at very close to the speed of light, but they're running at 0 frequency. And one of the things we're going to learn is that when you get very close to the speed of light, other people are going to say, you're dead, you're not moving. You're just like that, right? So those are two extremes that you can see just by this gauge geometry. Okay, it's a little bit ahead of what I wanted to do, but let's do it. Now, the next thing I want to do is really go over space and time. Not just space and time, but also per space and per time. That's what you're going to plot first. And I want to emphasize what is so great about that. It has a very famous name, and let's just clean this up and come through it step by step. The very famous name is Mr. Jean-Baptiste Fourier. Well, Jean-Baptiste Joseph Fourier, apparently. He's got lots of names. And he was Napoleon's sort of brain as far as wars go, or at least implementing the wars. Napoleon was brilliant and extremely stupid. Ends up on an island, banished from humanity. But anyway, Mr. Fourier is well known, and what I like to call this is the keyboard of the gods. So here we have per space time. So the time part of it is inverse time, frequency, waves per second. And if you look at the graph that you are about to plot on the left-hand side, you'll see waves per second. That's a hertz. And we'll get Mr. Hertz up here in just a minute. But then, and we're going to plot it versus the number of waves per meter. We're going to have a k vector associated with that. Where did that k come from? We've got to do a little history lesson here. But in any case, the person that's in charge of, well, not this. It's unfortunate Hermann doesn't seem to have used this, and neither did any of the other guys during the miracle wave. They didn't make very good use of it. But the basic idea is that this guy has his name on the hertz, so the inverse time unit is named after the inventor of a radio that could transmit voice. Let's get this one up to speed, and this one as well up to speed there. Okay, so the inverse of frequency is period, and that's the notation that we're going to be using for that. You can see it on that one, and let's go ahead on this one just for the heck of it. Okay, and while we're at it, we might as well complete the history lesson here. It's kind of interesting history, and I also want to go into what Hermann has to offer for a history buff. And we have a really brilliant history buff in our department here. Daniel Kennefic takes care of Einstein papers, but in the process he learns a heck of a lot more about the history of all of this stuff, some of which I picked up from him. So here's Heinrich Hertz, born 1857. This guy's born 4 years before this guy. They're both Henry, Heinrich Kaiser. K, that's where the K comes from. This is the kink axis, or the Kaiser axis. The inverse centimeter is the Kaiser. Any of you guys that work with chemists that do infrared spectroscopy, that's their unit, the Kaiser. Okay, does anybody know that? Physicists are extraordinarily ignorant of what the chemists are doing, and that's terrible. There's been a divorce that should not have happened there, as well as with the math department. But get off. I don't want to get off too far on this. Anyway, here's the per space-time done in blue. Here's the space-time that this guy was so good at visualizing. And wavelength is the inverse of the kappa, lambda, inverse of kappa, vice versa. Okay? So Greek K for Kaiser, I say kinks, number of kinks, and then omega, if you'd use the angular guide, and we'll do that later, omega, I'd say that's wiggles. Wiggles per second and kinks per meter. Okay? But a worthless mnemonic, right? But not necessarily worthless. You can use it. Okay, let's go ahead here and point out why I call this keyboard of the gods is that just this one plane here could be all bunch of keys. Every pixel here could be a key. Go in there with a little pin and push it and get a wave, a whole wave. Not just this much of it, but all over the place. If it's really a perfect keyboard of the gods, what I am going to be getting if I press this key, and I should add hold it, okay, and I mean hold it so that I actually get what I call 1 CW. That means a single continuous wave. Okay, that's what I'm after here, and I want that wave to go everywhere, and that's important. It continues everywhere. If this is really a perfect keyboard of the gods, I'm talking about no uncertainty in that thing. Now this is a weird thing. This is a musical instrument in the sense that I pick my frequency, but I also pick my wave number. I have all of that choice to make. So it's a two-dimensional keyboard if you even just have one spatial dimension. Of course, we don't know of any other time dimensions, so that kind of gives us a pair to work with here. And the idea is that it continues not just everywhere, but for all time. Okay, forwards and backwards. Okay, so we're talking about visualizing what one point on this graph makes over in space-time. All right. Now, next thing I want to talk about. This is first of all. Here's where you learn about the wave parameters. Wave frequency, nu. Well, the nu is related to the omega, the thing that I call wiggles. That is, the omega is 2 pi. 2 pi for every wave. One trip around the phasor is 2 pi. So we got an omega there, which I'm not mentioning right now. And then the kappa has a similar thing. The kappa is a k with the same ratio, 2 pi, for every kink. So I want you to make sure that those parameters are in. And then these are not so difficult. Time period, that's pretty obvious. Wavelength is pretty obvious, but it's very easy to leave a 2 pi out of a calculation that involves these things and be horribly embarrassed. I've seen it several times. Fortunately, it hasn't happened to me because I saw somebody else do it at an APS meeting, and that was terrible. So now I want to talk about velocity, wave velocity. And that's the thing that we'll be plotting in our little maps that we make in per space-time, and then that shows up over in space-time as a Fourier transform of something. So let's get this underway right here. And let's go ahead here and just see what it is that you do to think about the velocity, the phase velocity, the velocity of this kinky thing moving through time. Okay, and it's got a certain slope to it, and that slope is the ratio of the lambda to the time. It's just x over t, but lambda is the x of the wave, and this is the time of the wave. Okay, so that ratio right there, distance over time, wavelength over period, easy to remember, but should be in the deepest core of your relativity part of your brain. Okay, these are things that have to be right there all the time because you're always going back and forth between these things. Okay, so in this case, what I'm talking about is a lambda of 2/3. That's what I'm going to pick. 2/3 over 5/4. This gives me 8/15 meters per second for this wave. This is certainly not a light wave. This is some other wave, but okay, we're just getting used to the parameters here. So that I want to make sure is important. Now, wave speed comes out to be slope to horizontal in these graphs. Okay? In this graph right here, you obviously use an inverse thing. Instead of doing the space over the time, you do the per time over the per space. Right? Get the same velocity. Okay, so these are trivial things that we need to say. Now the Doppler is also fairly trivial, but it has some kinky little things to say about it as well. So here is us getting 8/15 meters per second some zillion different ways, and that's because we have 4 parameters. Not counting the angular ones. And the angular ones I can always go omega over k because they're both with a 2 pi. So that makes that nice. Omega over k is what we will probably be using more than nu over kappa. All right. Okay. Now, Hermann Minkowski was an academic superstar. He's about 18 years old and he's teaching a math physics class that has Einstein in it. Now Einstein wasn't famous then. And he was kind of a screw up. Hermann came in one day and scolded him, so you fat lazy dog or something like that. And Einstein turns out to be a little bit of a bigot. He's German and he's totally incensed by this person that has a Polish name, plus he's younger than he is, calling him whatever. This is a piece of history that you should know. And it did terrible damage, this little thing, because when Hermann Minkowski figures out how to make a space-time coordinate system, okay, and he does, because he's kind of following along with stuff that Poincaré is doing. He should have been the guy that discovered relativity and got it, so everybody could understand it, because he had a roadmap of it, and that's kind of what we're going to start to construct very shortly here. So we go 100 years without his discovery, because when he went to go to Einstein, all excited to say, "Look, if you can make a graph of your relativity," Einstein just go away, you Polish whatever. Okay. What's wrong with being Polish? Copernicus is Polish, right? Is he stupid? No. This guy's brilliant. Well, he publishes 1909 and he dies in that year of some weird disease. I mean, he's very young, dies very young. So we go 100 years with thousands of relativity books, not a single one of them having that roadmap in it, which would make so much clarity. Just the roadmap we're going to let waves give us, that's another wrinkle. Okay, if you excuse the pun. But the idea of understanding this weird thing that happens to space and time, this due to waves, that was not mentioned very well. They use pulses and things like that to do it. The key to relativity is Doppler. Doppler is the first relativistic effect. It's first order and really easy to understand without much of a roadmap at all. It's Christian Doppler sitting here worrying about sound, worrying about that a strange thing that happens when a train goes by. Or of course, if you're hitchhiking, that's what you hear all the time, right? Meow. Oh, fuck, he's not going to pick me up. Right? So, an airplane. You hear it all the time, you get used to it. You don't realize what's going on. But that is the key to everything we're going to do today. And the very basic idea is that we're going to have an atom going through a light wave, actually 2 light waves, that's what you need to really get the relativity going. But the atom is traveling along the wave. You think of a boat traveling with the waves that have been built up by a big windstorm. You probably want to take a ride on that boat because you don't hit the wave and you do not collide as often, this is a long time here, as it would be if you went, stood still and let the waves wash over you and hit you here, here, and here. That's a little quicker than here and up here, okay? So we're just looking at the intersection of your track with the track of the waves, right? And here they're close together, far apart, and very long time. I mean, here's a shorter time, and then if you're going to go into the wave, bam, 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 real fast, right? So this is a crude picture, and the basic idea of it is, and this is what we're going to see, if you move fast enough this way, that is, if you get up to the wave speed, and we're talking about light, that light wave will get redder and redder and redder, that is, becomes black, until it dies. The opposite thing is to try to go at that speed into a light wave. Move fast enough this way and it gets bluer, and I mean into the UV and the hard UV, the X-rays, then the gamma rays, and you aren't even started yet, it's going to kill you. So you have two choices here. Have the wave die. And what's really interesting about this is we're going to see later on that frequency and amplitude obey the same Doppler relations which we're about to derive, because the amplitude is a frequency too. That's the second quantization. Amplitude is quantized, as well as the Ks and the omegas, if you trap light. Okay? So that's what we're getting here. So there's this relation, nu over kappa, omega over k, lambda over tau. That's a C that you would use for sound, but the one we're going to be doing is the big guy. Okay? And so we're going to be rescaling, and you're going to be seeing that for a space-time diagram, I want to plot lambda versus c tau, and for frequencies, I want to plot frequency versus c kappa. So the time graphs are going to have a c put on this axis. The space graphs, the inverse time, the per space-time graphs, are going to have the c put on this axis. Okay, so that both axes turn into frequency. Now, of course, you could both make them Kaisers, but not very many people know Kaisers. That doesn't done very often. Okay, let's get started here with Dopplers. What's so cool about Doppler? And this is where it's very popular now if you're dealing with optical information theory and things like that, that you involve two characters. Bob, I like the earrings, and Alice. They're both cool, okay? No question about that, right? These are top-notch physicists and really cool operating physics. So what we got here is Alice has got a hold of a source, an infrared source. 300 terahertz is right sort of smack in the infrared, and she is moving really fast. You have to imagine this graph is, hundreds of parsecs even. I mean, there's a huge distance between them, so they don't run into each other. But the laser is powerful, so the light that she's making, which is invisible light, is infrared light. And whenever I want to show something moving, I use speed lines and try to, tilt it. Okay, so we see a lot of pictures like this for Bob and Alice, and we have another character, Carla. She's kind of sketchy, but we need three, A, B, and C. We need more than what you usually have for quantum optics. So anyway, here's Bob just sitting here, and we're looking at what's going on for him. That's why I drew this to be what this looks like is a green light. 600 terahertz is what he pulls up on his frequency meter, and he tells. They're talking on the cell phone. He tells Alice, I got this beautiful blue-green, and it's 600 terahertz. And Alice says, okay, Bob, that's what I figured. What's your wavelength? That's a completely different measurement. Okay? You got to fit it in some spatial thing, right? At least. Okay? The frequency meter might be using some fancy atomic transitions or something, but to get the wave length or the wave number, the per spatial part, that's tough. So approaches Bob. Bob sees 600 terahertz, and the question is, what lambda does Bob measure? And the real question that's kind of behind this philosophically is he seeing a phony green? This was produced by this cheap 300 terahertz laser, right? It's cheap light. Now, she happens to be moving, okay. But this is in the future where it doesn't cost you very much to go fast. So, is there something about this green that's weird? Should I get a funny reading for this? And that's what I'm plotting here. Here's the frequency, the same graph that we're going to work with, ranging from infrared up into the beautiful blue-green. That's a wonderful color. It's the color, I can't produce it here really, it's more like that. It's the Caribbean Raman scattering light that comes with the very pure water. It makes swimming pools turquoise blue. But these are higher frequencies which you can't see here, and you really can't see very much. The actual visible is about there and there, but I'm using color sort of loosely here. In any case, the question is, he knows he's got 600 terahertz, but where in this graph is that light supposed to be? Okay, so let's push ahead here. The figure there is out of that chapter 0 paper, which I recommend to you as the shortest way to get to this stuff. But anyway, years of spectroscopy rule out a phony 600 terahertz like B or D. And in so doing, it's saying that that green had better have the same damn speed as any light, but in particular it ought to be this choice right here. So that's the real point here, is that this whole idea of having this speed that now we think of it as being stupid. We're thinking of the Galilean transformation where I said, if I go this way 3 miles an hour, everything in this room gets an extra 3 miles an hour. And so that light's going to have that 3 times 10 to the 8th meters per second, no matter what I do. Okay, so that is what you see here. This would be slower light, less of a slope. And this would be faster than C if it was over here. Okay, so that is one way to, in a sense, logically prove that all light, and that includes green, red, blue, whatever, basically the way to say it is all colors go the same speed. That is the only axiom that we're going to use for this whole development. That's it, right there. We're going to build everything from that. Now, as I say, this is 3 times 10 to the 8th. We're going to take 3 times 10 to the 8th. In spite of the fact that my dear friend Ken Ebenson went to a lot of time and effort and was told by his bosses that he was stupid for doing this, measuring light 1,000 times more accurately than it had ever been measured. But in so doing, he changed the world. Because what they did is he got him to have a meeting at the units, the metrology conferences, and he said, you know, we ought to use this number as a definition of the meter. Because we really can measure time accurately, and it was getting better and better. Now it's 18 figures. He was really happy to be getting 9, 10, 11, even 12 figures. That was just, oh my God, how did he do that? By coupling a whole step of lasers of different harmonics. And that took a lot of work, and it was told, stop wasting your time. Well, that was time well spent. Because once we did that little change there and measured the meter in terms of his number, we could do GPS, we could do incredible spectroscopy, which I benefited from. There were a whole bunch of things that all of a sudden fell into place. And they continued to do that. And one could argue that the quality of the oscillators, I've said this before, is matched by the quality of civilization. Which one causes which? Well, that's for you to decide. But this is the point. All colors go the same speed through the vacuum. This is dispersion free. And dispersion means that the colors don't get out of step with each other. And that is absolutely essential for what we're going to be doing here. You've got to stay on this line with a 1 CW. But you got 2 CW, you can go anywhere. And that's what this is all about today. But we got to get there. Okay, now, I should point out that there is another way to show that sort of thing. Is for those of you that are astronomers, you should be aware that when you go out at night and look at the stars, first of all, they're not going anywhere. It's just frozen out there. There's no huge explosion can make something, say 50,000 light years go like that. That would be many thousand times the speed of light, just to do that, right? And light coming to us from something that's 9 billion light years in the past, and we have the Hubble picking stuff like that up, comes in without making a rainbow. Think about if the blue is just a tiny percentage faster than the red. The blue would show us this galaxy in its early stages, sort of in nice shape, and the red would show us all blown up or spread out or something, right? It would just be a mess. You'd have no astronomy if we don't have this axiom. So this axiom is not a mystery. It's not a kind of, well, he said so. Einstein was really smart, so he knew, right? That's not the way we do physics. Okay, now, this is the important thing that involves Carla. Carla, as I say, she's got some zip to her there, and she's headed that way at some speed relative to Bob. Bob is the main character here, so we're looking at what he's seeing with these two galaxies, a shining light, or basically right now just receiving the light from Alice, who's zipping along at a speed that we're going to be calculating here shortly. The idea is that we make a little thing that's kind of like quantum mechanics, where you have something that starts on the left and ends on the right. So I put the ratio of the frequency of the receiver to the source as R over S. In other words, I actually think of that line as having a little slant to it. This over that. Always the source is in the denominator for this definition of stuff we're going to talk about here. And the logarithm of that ratio, receiver to source, is the rho that we were talking about earlier, that makes the hyperbolic functions we'll work with in a fairly standard way, actually. And it has a name. It's called rapidity. You don't see it very often. It's just kind of hidden in some papers. They'll talk about it and then it goes away. This is really important. Rapidity, having a logarithm, is really important because, for example, if you ask how fast is going a proton in the European Hadron Collider, and it's 9999999, roughly. I mean, it's a lot of nines. And who wants to do arithmetic with all those nines, right? Well, taking the logarithm of this thing, the Doppler shift is also quite extensive for that, and lots of numbers. But the logarithm, is about 7. The hadron is up to 7 in rapidity. And compared to things that are out in space, that's nothing. That thing's a little toy compared to what's going on in some things. And every once in a while, one of these things comes through the atmosphere, and we realize how much energy there is hiding out there. Anyway, that's the number that we play with here. And what I want to show you is that that particular quantity, using that as a measure of velocity, is really cool. because then Galileo, who we've completely defeated here, comes back. And he gets to do his sum rule with rapidity, and it works perfectly. That's what I want to. I'll make sure I show you here. So here I am doing 600 over 300 for Alice as the source and Bob as the receiver. Okay, so it's a 2-to-1 ratio. And then the rapidity is a logarithm of that, so that comes out to be a decimal. Fraction we started with was not, wasn't rational. And then I could do the experiment in reverse, and I would have the person with this laser being receiving from, if you turn this into a laser and send the light back, that would be the logarithm of foot. That would be minus. So the relative velocity, Bob to Alice, Alice to Bob, okay, that is what we're talking about here. And meanwhile, Carl is down the line here picking up Alice's light as well, and we're seeing a 400 over 300 ratio for her, and the logarithm of that is 0.2876, okay? So, let's take this ahead here a little bit and show that Galileo's Revenge, this is part 1 of his revenge today, rapidity adds just like Galilean velocity, because if I'm answering the question here of what we really are asking here is Carla's rapidity relative to Bob. How do you get that? Or in this case, I'm talking about Alice Carla Doppler ratio. Well, here's the how I use that to get Bob Carla Doppler ratio. I just say, okay, I've got Carla over Bob. Well, let me just stick in Alice off the diagonal. This is our chainsaw sum thing again here, but a really elementary version of it, right? Okay, so it's the product of these two. It gives me 2/3. Well, that's kind of what we're talking about here. 2/3. Okay? So if we put it in an exponent, which is what we do to get the actual Doppler shift, the Doppler shift is given by the exponential of the rapidity, they just sum. Bingo. I can, you know, this is the only picture I can find where Galileo is smiling. All the rest of him, he's really grumpy. But here, he's had his revenge. He was right all along, he just meant rapidity. It works perfectly. And that's because it's a group parameter for the Lorentz group. That's the way you could say it. You're going to be a mathematical about the whole thing. Okay? All right. Well, we've got a couple more revenges for him coming up here, and that I couldn't find any bigger smile for the guy, so we'll have to do the one we've already gotten and talk about interference. That is what makes us have our relativity coordinate system and eventually our quantum mechanics, the whole stick, basically, for this. So, what I want you to realize is that when we ask what's going on with two phasors, one of them, say, a slow speed of red, infrared, and then I got green here with 600 terahertz, it's only 300, or something like that. This one's going around a lot slower than this one, and so eventually they get close to each other and they make a great big lump called a beat, or a group envelope, the top of the group envelope. And okay, that's something I think that you have seen already in any sort of, anybody talking about wave interference. But we'll take it a little bit further, because what I'm saying is that you can look at that from the point of view of, say, the red beam. Let's just let the red beam stand still. We'll just add a frequency to everything, and that you can do. You can add your phase. You can make relative phase the important thing, and then have any value that you add to all of them, it'll still be the same physics. So this is kind of a beginning of gauge invariance and all that kind of stuff right here. So real quick, let's go back to the old Pirelli site that we had and show the two right next to each other, okay? So what you're seeing here, and this is the diagram I want, that's the thing that we're going to be part of our roadmap before we're done here. But anyway, here's the green guy going real fast compared to the red guy, and every once in a while they get opposite each other, and then a half beat period later they get in cahoots, and so you have an oscillation. Same oscillation that you have here, okay? But it's got this weird Thales structure there. You see that diameter rotating there? Always a right angle to the very last, and then a minus right angle, and so forth. That's important. That's Galileo's second revenge right there, is that when you interfere two waves, you get to add their phases. And I don't care how fast these waves are in frequency, or how fast they're moving. It can be a sound wave, they do the same. The rules are the same for that. Now, this particular one here, if I can bring this thing up, I think I can go back here. Let's see. I would like to show
I don't think you hit it square.
the actual, let's go. I'll just go to the home of this thing. I'll go to the sitemap where that thing is. Then you should learn how to use the sitemap, and I have to refresh my memory how to use the site map. But what I'm looking for are the beats, and I believe I'm going to find it right here. Light means light, and you just go clicking along here. There's a typical red versus green, or combs versus each other. If you want to teach beats, that's a neat way to do it on an overhead projector. Here you can see how they add up and then subtract and so forth. Okay, and it's a difference over 2. That's really important. Okay, and that's sort of the geometry of the thing right there. There's the half sum that we're going to be working with very shortly here. That half sum is really important, and here it's like that. Half sum and half difference. We need both of those concepts. Okay? So what we're going to do is we're going to be doing an analysis of the group wave, making a coordinate system, and we're going to be doing it by factoring a sum. This sum right here. Factoring it into this times this. Okay, so this group apart, the difference is something that's real slow. It's got a long wavelength, slow frequency maybe, but certainly it's a fat thing compared to a much more wrinkly thing. That's the sum. Okay, so the product of those two, which is the way that we end up getting that factors those, the two factors give me this. Okay. So they're the guts of the wave, which we call the phase, and then there's the envelope we call the skin. Okay, we're being using medical terminology or something here. Okay. All right. So that's worth seeing, and then the geometry of the one where it does the Thales construction is really important. Okay. Back to the lecture here and forward. Here's where we actually make this stuff right now. And this is where we're going to be doing the construction of what the interference is. But first, it's really trivial. It's a standing wave. But what does a standing wave have? It has a coordinate system. That's what no one seems to have taken advantage of. The fact that I put one CW coming from the right and one from the left, this is what I get. Okay, so I can do this simulation, I think, immediately here by clicking on this. Let's see what happens, just for the sake of fun. Okay, so here is a wave coming in with the imaginary part, imagination preceding reality by pi over 2. Another one coming, so the imaginary part is on the front side of the motion. And what we're making is a wave that every once in a while, the real part of that wave is bang everywhere. Right? The phase of this wave, which I'm indicating by this as the half sum, of a baseball diamond. And the basic idea is that we're going to be constructing what we get in a baseball diamond in which there's a Doppler shift. But right now there's no Doppler shift. I've got 600 terahertz on both these lasers. They're both the beautiful blue-green laser. Okay? So, as shown in the middle slide there, or the far right, the sum, 1/2 of the right-hand amplitude plus the left-hand amplitude, that's what you're dealing with for this thing. And this is first base, this is second base up here, that'd be the sum of the two. This is third base over here, P for pitcher's mound, okay? Nice mnemonics, all right? Meanwhile, I used to call this the dugout, but then Woody across the line says, hey, no, that's the grandstand. G for grandstand. Okay, so now I've got it in the front of the word, full mnemonic. And that's what we're going to see. We're going to see how all of these quantities, the grandstand, the right, the left, the first base and third base, and the pitcher's mound change as I run through this thing and Doppler shift one of these into the blue and the other one into the red. That's the whole trick right there that makes this possible for us to do what we're setting out to do here. Okay? Now this should be easy stuff, so if there's something here that you didn't catch, now's the time, ask, because we're going to be doing this for another 2 days, but we would like to use that time efficiently. Okay, so if you have something that you know, I just think it's wonderful that in the per space time, and here I'm writing angular frequency and angular wave number, 2 pi times kappa, 2 pi times nu, 2 pi for every one of these phasors down there. Rotation gives you a 2 pi for the kind of frequency we use to calculate everything that happens to waves that involves that interference effect. Well, this guy is straight up, that's got a slope of infinity, and that's what this does. Bang! It's everywhere. It's going infinitely fast for an instant there. And that's what you need to make a coordinate system. In order to make a coordinate system, you really need the phase, the heartbeat of the wave. Makes the coordinate system crossbars. Otherwise, you just have these guys straight up. That's the group. The group part here has 0 slope. Okay? And that's what a reciprocal space does for you. It's turning everything up here upside down in the arithmetic. So we have 2 points on this keyboard of the gods. And you can see, by doing stuff like that, making these different, I'm going to be able to cover the whole darn space. I can use every key on the keyboard of the gods piano. I don't have to just confine myself to one line here and one line here, or in the other, a line coming out of here for the other another dimension, right? That makes a cone. That's called the light cone, right? Just to get you connected with what you usually hear in relativity. I always talk about the light cone when they hardly ever do much with that cone. Okay, so let's go ahead here. Now this you can look on your own time. It shows you a little bit how to use the control panel for Boret that's making this particular graph. And there are all kinds of very strange graphs that you can pull up and play with in this scenario that we have. Here is a more explicit picture of the arithmetic that's going into making this. And the basic idea is we're adding 2 phasors. We're adding 2 e to the I something. E to the I some phase, and then e to the I a phase with a sign changed on the K. That's the only thing that's really going on in this. Let's see if I can say anything more. I think that's basically it. I'll use the center screen here for the arithmetic. Okay? So the arithmetic, we've already done this once when we were doing the waves in a mode for 2 oscillators, and just two things. This is an infinite number of things, and I've got it set to just show it with 24 or so phasors. But the basic idea is to factor this thing and find the zeros, right? That's what factoring involves. I want to find the zeros of both the real and imaginary part, but I'm really keying on the real part today. The sum, half sum, times the half difference gives me that one. And then I put a minus sign on that one right there. What does that do for me? Okay, well, that gives me this guy right here when this is multiplied by that. Gives me this guy. So there it is, factored. And this is the phase part of it right here, R plus L, sum. That's the arrow that points up. And then there's the difference over 2, okay? So that's this thing minus this thing, which would be, you know, down there. But that would put you over here. Half of that is what the G is. Half of R minus L. Okay? All right. Okay, now, this is a lecture on space and time, and I'm seeing time does what it does. It gets short. So we're going to do a little bit more here, and then we'll just continue. I'd rather go so that everyone is following this than rush through it. And yeah, you see that there is, well, it's simple. It's not stuff that you're used to. I'm going to pause this so I can change back to this and do what we really came in here for. And this is the thing that you're going to, I'm going to ask you to actually construct this on the graph that you have. This is just showing a picture of what we're doing compared to what Einstein had in his head, apparently. Michelson and Morley had definitely in their head is the idea of pulses. Pulses are really simple, but they don't interfere with each other except when they cross, and then it's a most ungodly interference. It's an absolute mess, and then they extricate themselves and continue on their merry way, making an actual baseball diamond in space and time. But it took a lot of Fourier components to do that. That's really complicated. This is simple. This is really simple. Left plus right gives me P and G, a coordinate system. An actual lattice in space and time from a reciprocal lattice, which is what this is. Okay? It could be. I could keep adding to make that thing. All right? Okay, so let's go here and do a Doppler shift. Now, I'm talking about rapidly moving Bob now. So I'm going to make Bob move so fast that he turns the 600 terahertz into 1200. Okay? So here's where you draw your first lines on your graph. You have already a 45-degree line, just like we had a 45-degree line that was so important in our very first graph we drew for the collisions. So this 45-degree line here doesn't stop at R. It will continue all the way up to here. And I guess the best name I can give that is R with a prime on it. So that would be what you would draw as an arrow making first base of this baseball diamond into a marathon. Okay, so what I'm going to do here is I'm going to just draw a, if you had colored chalk like I do, you would use a violet color in order to finish this particular, thing. Now the question is, and this is something that comes out of that Doppler analysis by Rapidity, is that if I get this Doppler shift by a factor of 2 by running into this laser right here, this is the laser that's on the right, sending a left wave. That's the thing that's a little confusing about this. So I'm running toward this 600 terahertz with enough speed to get it up to 1200 right here. So cross out the 600 and imagine that it looks like a laser that's putting out 1200, okay? Now the thing that I have proved by doing the rapidity dance that we talked about, but this is something I'm going to skip for now. You can read about it in the description. Any one of the articles we've written about this stuff is if I double this one, I've got to have this one. In other words, this one got blue shifted, I mean really blue shifted. That one's going to get really red shifted by the same factor, 2. And it's going to be half as big. So this one is going to end up over here with looking like, it's going to look like 300. It's going to look like infrared. It's going to look like a nice warm breeze in the summer. Okay? And so it's going to be an arrow that is this big right here. So just draw a fat arrow. If you have color, you go home later and make this a good graph. And this graph paper is on the web, so you can make all sorts of different diagrams. But the basic idea is now you're going to have a baseball diamond here that has a long marathon to first base, but it only has this much distance to go to second base. So here's the line that you need to add to this to get this exactly right. That is, you have to bring this thing exactly along the diagonal there. In other words, I want to draw a line right along this thing right here. And you can use the graph to help you. I've gone too far with that because I've got to use my compass here to figure out, make it figure out how much length I have to that point. So use your compass to mark off on this line the other side of what is now a rectangle. Okay? So I put the compass right on the graph point, and I get right about there. Okay? So it's a short steal to second. Very short. Poof, you're there, right? But try to get third now, right? Going to third base, oh my gosh. I mean, I'm already tired from doing the first 2 bases, so it's going to be a real problem doing that one. And I won't use this clumsy ruler. I'll use the one that's stuck to the board here to come down to there. Okay, so what I have to do is put this thing right down the diagonal of the graphs from that point right there, and I have little marks on the board there to tell me that line. I'll use blue for it, just for the sake of argument. Okay, so down, 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 down I go. Not quite there yet, but you can see it's a long run to get to there. So we get a nude baseball diamond. We get a baseball diamond that is what a baseball diamond looks like when you're sitting in a grandstand. If you're over here, it's perspective, okay? Isometric perspective, that's exactly what it would be, all right? So what we need to do now is find the pitcher's mound, okay? Now that ruler isn't quite big enough, so now I really have to use this monster here to find out, first of all, where this diagonal is, and then where this diagonal over here is. Okay, so I need both of those diagonals to finish this diagram, because I've got to get the half sum and the half difference. This is the sum right here of those 2 vectors. So I'll draw that right away. There's the diagonal right there. And that's going to contain my new phase vector. And then I've got to go the other way to get the diagonal that contains the group vector. At least just a vector that's pointing in the direction. It's really nice to have that magnet. When you don't have it, of course, gravity takes over pretty easily on these, and it's warped, so it really is bad. So you have an easy job here compared to what I'm doing. And this is, you know, in the future when we do this geometry, we'll of course do it on a computer. So I drew most of the drawings that are in the slides. You know, here, you hold, I'll draw. I've got to go about, I got to go up to there. Has that got it? Okay. I'm going to go ahead and draw that. Okay? So one of those vectors is in the right place, that is with its rear end on the origin, and so you use an extra thick line on it. I'm going to put this guy away and bring back my nice magnetic fellow here. This guy right here, this is going to be my new pitcher's mount. Pitcher's mount used to be there, now it's going to be here. It's going to look like it's there. That's a big change. Okay, so here's the, and I usually use blue for the phase vector, dark blue on the screen. Okay, so there's P, and since we already used the letter P for the original P down here, this will be P prime. Okay, this is what you would see if you're Bob going this fast. You're going to see the your phase vector sitting there. Now, you can use your compass to get this vector right here moved down to the origin, so its rear end is on the origin. Best way to do that, even if you didn't have graph paper, right, was to just measure this distance right here from that point, this distance right here, and strike an arc down here, and then put the ruler along the perpendicular of this rectangle. Okay, and that is about right there. And that should give you, I'll go ahead and just put a dotted line on that. I'm not interested so much in that line for anything physical, but that's about where it ends. And that is the point that the group vector is going to occupy. Make sure it's pointing at the origin and pointing more or less where I want it to go. So this is going to be the group vector, which I use green for it, dark green, but I have a light green here, which is pretty obvious. Okay. So there, make it a sort of a dashed line. There is my new G. The old G was down here at 2. This new one is right here above it and off to the right. Now the other thing that we need in this construction is to finish the basic unit cell. It used to be, I don't actually need to use this little thing. I can do this with the magnetic one. I need to put a ruler from the G to the R. That stands for the right laser, right moving laser. This is the left moving laser. Right one's over there, and we're moving in such a way that we run into that line. Okay, so let me finish this one with this. Okay. So that's the new per space-time graph that's predicting where our coordinate lines are going to be in the space-time graph. In other words, those are the unit vectors now for the reciprocal cell. That's what this is. And what we're going to be seeing where Bob is standing, when these two, the UV light here runs into that one, okay, we're going to see something quite different. So what I'll do is I'll go ahead and start the simulation for that and hope that it works. We've been having trouble here. Here, that is.
Go one more page forward. Those were the models.
Let me go pause that one. Go back there.
Go one more page forward. That's just the one
Yeah,
CW.
that's just showing one thing. There's that guy,
bottom corner.
and that one should work, right?
That also has your P and your G there labeled. Really
So we're
good.
talking about, whoops. I've got to get it on there. There we go. And there's Minkowski. That's a Minkowski graph showing everything there is about relativity in terms of space and time. It shows that the length that I had before has contracted. It shows that the length, there's a little parallelogram right there, okay? Shows that this, this point right here has moved over, does the same thing in per space-time. The only thing that's different is that now the phase vector's down here. It used to be infinitely fast, pointing that way. Now it's just very fast. And then this vector right here used to be 0 speed. Now it's very fast. How fast? We can look at the graph and see that. That's kind of neat. The slope of this line right here on your graph, if you've drawn it correctly, the slope of this one right here determines the phase, determines the group velocity over in space-time is 3/5. That's how fast you have to go to get an octave of Doppler shift, a doubling of this frequency, and halving of the other frequency. So we've just, I mean, too bad Minkowski couldn't see this. I wouldn't have to do any work and be part of the lore. But that's the basic idea of it. And then the really screwy thing about this is that the stuff that was infinitely fast, the stuff that we call now in this graph, it now tips. So that you get to see on this side the past of this somebody moving through space and time. And on this side you get to look at a little bit of their future. So everything on above that line is the future relative to that particular value of this observer's time. So we'll say more about that later on. And we'll talk also about the Einstein time dilation. It used to be, the square used to be about this big, now it's this big. The square that's drawn on your graph paper isn't a square anymore, it's a rhombus. And it's this rhombus right here. Now in the time graph, you simply draw this again, and again, and again, and again. You just make a whole lattice of these things, which is what you're seeing. The whole lattice of the parallelograms, the rhombus, the equilateral rhombus is a name. Rhomboid, I guess, equilateral rhomboid, whatever you want to call it. So that's the really deep thing that I should stop with, is that we now have special relativity basically handed to us. Now, the scenario that gives you that wave, I can think of 3 ways to do that. 2 really expensive ways, and 1 no problem, practically 0. If you've got the equipment already in lasers, you can do this right here. This one is to get both of these girls going at 3/5 the speed of light. Carla shines back at Bob, she shines forward. He sees Alice's beam 1200, that's a horrible UV, better be wearing protective equipment. But 300, oh, it's just a nice warm breeze, thank you, Carla. The other way to do it is get Bob off his ass and make him go 3/5 in the other direction. okay? Pretty much the same thing. It's just that when he does that, we got to remember, and this is what's really cool about all of this, is everything we're calculating about the frequency changes affects the amplitude in the same way, because the amplitude is the frequency too. That needs more words put behind it, but that's what's going on. Okay, so this caused how many billion gross national products would it take to get Alice up to 3C5? A lot. And it'd be twice that to get Carlos going up to, so this is really expensive. Here with Bob, okay, given he's maybe goes to the gym a lot, so he's not so heavy, we can get him up to 3/5 for, you know, say, gross national product of Paraguay, okay? And then, but that's impossible. We can't get that money. Maybe Trump can. But anyway, Bob's stationary, Carla tunes down, Alice tunes up. That's the way to do it for nothing. Same thing, except for the amplitude, which we'll play with later on. And you can always put neutral density filters in to bring the amplitudes equal. It is essential to get equal amplitudes. You get really crazy behavior when the amplitudes change, and that's what you can see by playing with Bohr, changing the amplitude a little bit. You get things that, well, you get tracks that look like antiparticle creation and destruction. That's what happens. So, you know, we're on the verge here of playing with some pretty hairy stuff, just by playing with waves. Okay, so we've got more to do. Now, is this, I'm just sort of, you know, what do you think? Do you feel good about this, or do you want to go back to the old notations? Because the numbers that we're going to put down for these wave quantities, the kappa of the group, the lambda of the group, the frequency of the group, the velocity of the group, okay, and then the period of the group, and that. So this is all group stuff. And then there's the phase stuff, same thing, velocity of the phase, the lambda of the phase, happens to use the same numbers. This nu of phase here is the same as the kappa of the group. Lambda of the group is the same as the tau of the phase. That's, you know, something we look at when we look at the algebra carefully. It's because it's a rhombus. Okay? So basically there's a cosh, because we do half sums and half differences of the Doppler red plus the Doppler blue and minus over 2. That's what gives these things here. But meanwhile, perpendicular to that motion is a light wave that's changing its sigma angle. And those are the changes that it undergoes. So we're taking care of that as well. Two birds for the price of one here, because the trigonometry is both hyperbolic and circular at the same time. Cool? I thought so, but then I'm biased. Okay, well, we'll attack it on Monday, but in the meantime, go ahead and finish. Because I'm going to pick a random speed, some sort of speed, and you're going to come in on exam day, which is supposedly 3 to 5 p.m. You won't need anywhere near that much time, I hope, once you know what we do. We've got half the number of lines we need for the complete destruction of everything. I mean, we've got Lagrangian, Hamiltonian, it's all in there. They're all hiding in there, all this stuff. It's all hiding in this crazy little geometry. Okay.